Okay, welcome to this video. We are going to talk about energy and energy transformations in a simple harmonic uh, motion system. We'll look at this mass spring system as our example, do some analysis. We're also going to fill out these notes, which you have. We'll fill out this entire front page, and that'll be it. Okay, back to the simulation and our observations. First, let's just observe what's happening. This thing goes back and forth. There's a left edge and a right edge to its path. At the left edge, right here, the spring, the black part, is really scrunched up. It has maximum compression at the left edge of the path. At the right edge, the spring is really expanded. It's been stretched. So it has maximum stretching. What can we say? We can say at both edges, where the displacement has reached the maximum value, the amplitude, at both edges, the deformation, which is compressing or stretching, is at a maximum. Because deforming a spring produces potential energy, if you have maximum deformation at those edges, then the PE, the potential energy, is also maximum. What about the speed at the edges? At the edges, we turn around. The thing is actually switching from moving left to moving right, or it's switching from moving right to moving left. And so for a brief moment, in order to turn around, it has to stop, which makes the speed 0. If the speed is 0, then the kinetic energy, which is 1/2 mass times speed squared, the kinetic energy is also 0. What about at the center position? The center position is where we have 0 displacement. At the center, you may know the speed is at a max. And here's why. Imagine that we're at the left edge and we're moving over toward the center position, which is maybe about right here. As we move from the left edge over, we speed up. When we get to the center, we have been accelerating the whole way from the left edge. Once we pass the center position, we start slowing down because of the expansion, the stretching. So at the center, we are moving the fastest because that's where we've been accelerating the whole way there, but we haven't yet started slowing down. So at the center, there is maximum speed, which means there's maximum kinetic energy. On the other hand, at the center, that means we haven't stretched or compressed the spring, so the deformation is 0, and hence, so is the potential energy. So let's summarize this in our notes. As a particle or system oscillates with simple harmonic motion, the energy is continuously being transformed between kinetic energy and potential. We have equations that let us calculate how much kinetic energy there is. The equation includes mass, angular frequency, amplitude, and displacement. So if you know the displacement at some moment in time, you can plug that value in and you can calculate the kinetic energy at that moment or for that displacement. Move over to this equation, this one. The total energy depends, as you see, on the mass, the angular frequency, and the angular frequency squared and the amplitude squared. That's what it depends on. When the kinetic energy is at a max, all of the total energy equals kinetic, and so you have this, the maximum KE, is simply equal to the total energy. equation that you're given for potential energy. You probably won't need it, but just in case, I want you, right in this space, to derive an equation for potential energy. And how do you get it? Well, write down on your page, something over here. At any moment, the total energy equals the kinetic energy plus potential. Therefore, the potential is the total minus the kinetic. So write in the box, or in that space, an expression for potential energy, and you're going to want to subtract this, take this, and subtract from it this, to get the equation for potential energy. Again, you probably won't need it, but just in case, let's try deriving it, just as practice. Now, let's say a system has a VT graph that looks like this. Velocity is on the y, time is on the x. Right? What about the total energy as a function of time? Well, this is really straightforward. Believe it or not, the total energy remains constant. So even at half of a period or a full period, at all moments in time, you have the same total energy. But clearly something changes, right? I mean, something is changing here. If not the total energy, something changes. It's the kinetic energy and the potential energy. Those are what changed as a function of time. So what about kinetic energy, EK? Let's try that again. EK. If our graph for VT looks like this, then you see at time of 0, right here, kinetic energy is going to be 0 because there's 0 velocity. When you get to here, kinetic energy is at a maximum. And it's positive because you can only have positive kinetic energy. Whoops. Let's try that again. Then right here at half of a period, where are we going? Let's come back down here. Okay, so then at half of a period, right here, the kinetic energy has gone from a max back to 0, so it looks like this. And then when we get right to here, we are now at a maximum speed. So we go up to a max, and after one full period, we're back down to this. And at these moments, and this is time on the x-axis, at these peaks, we are at the center position. At the center position. Because that's where we're moving fastest and have most kinetic energy. What about potential energy? E potential as a function of time. This couldn't be easier. Just like the kinetic energy, it has to be positive. We make it positive. And so, if we have 0 kinetic energy, that means we're at the edge, where it stops the spring, and it means potential is at a max at the edge. Where kinetic is at a maximum, that's the center, right? We wrote that down. And at the center position, there's no compression or expansion, so there's no potential energy. Again, when there's no speed, that means we're turning around, changing directions. We're at the edge, so we have maximum potential energy. Then we come back here, and then back up to here. So here's what that graph looks like. Notice, for one full period, and here's half a period, for one full period, you get at least 2 spikes. 1, 2. On potential energy, we have 3 spikes. And also notice, you never dip into the bottom negative half of the graph. because the kinetic energy and the potential energy we say are always positive. But remember, E total is constant for simple harmonic motion. The next thing we'll study is damped harmonic motion, where energy is not constant, total energy is not constant, but where the energy is reduced. But for simple, though, for simple, not damped, we have constant total energy.